So it should be recorded, and it's not there. What's going on? I'm sorry, something is not working, so I'll try to restart. Guys, looks like that for some reason it's not working, and I don't want to waste time on this. So what is a good idea? The class size is not too big. So how about this? If you can come closer, I can show you that what I want to show you. Thank you so much. Sorry, I created trouble. Maybe you can let's put it here. Okay. Please come closer. So if you see. Okay, so what we're going to see is some animations that will tell you that what is the different states of electrons if you put it in a quantum well. Okay, so this guy is trying to, let's see if I can make it bigger.
Website? Or?
This is a website, yes, and it is there in the slide, so you can see it. So they're trying to show what happens if you take a quantum well, which looks like this shape. Okay, remember, and the potential wells are created by what? Who creates the potential well?
It's from the nucleus, right?
From the nucleus, yes. Okay, nucleus draws the electron, and that's where the potential well. So whenever the potential goes low, that means that there is an nucleus sitting there, which is trying to pull the electron close to it. Okay, so as you try to go away from the nucleus, your potential goes up. Okay, so once the electron is being attracted by the potential well created by the nucleus, it will not go to arbitrarily any length. Okay, there are some certain energy levels where they can sit. So it's like if you bring some people in the class, they cannot sit arbitrarily any places. There are some certain seats, okay? So similarly, an electron has some certain energy seats, okay? It's not real space seat, it's an energy space seat. So electron can either go into this line, or it can be here, or it can be here, but it cannot take any arbitrary energy space. So with that, let's see. If I make this potential well very narrow, let's see if I can bring it down, you look into that what is the impact of different energy states. Remember, all these different energy states, it starts from here. For instance, if I put n equal to 1, you will have the lowest energy. Okay. For n equal to 2, it will have second energies. N equal to 3, n equal to 4, it keeps going on. So for the lowest energies corresponds to this level, okay, showed by the blue lines, green lines. And this is the next energy level. This is the third energy level. And look at that, the corresponding wave functions. So for the very first level, then the wave looks like this, okay? It has only one dumbbell shape. For this next energy level, it will look like this. For the third energy level, it will look like this. Do you see that every time you go to higher energy level, the dumbbells, the peaks, it keeps increasing, right? And also, look at the spacing between each of these energies. As you keep going up and up, the spacing also increases, right? So if I make these well wider, okay, what's going to happen to those energy levels? Let's try to understand from these equations first. Let me just put it up. One over Poisson square. So L is the width of the potential. So if I increase the L, your energy is going to go down, right? And also the spacing between these energy levels, they will also become closer. Okay. So this is what you will see here. If I make these well wider, these spacings, different energy spacings, they will come closer to each other. Do you see this? They're coming closer to each other. So if you make it really, really wide, all these spacing between energy will be just smeared out. There will be no spacings. So that is what we see in classical domain. That's why in classical domain, we can attain any possible energies, okay? Because there is no difference between all these levels. If you go to quantum level, only then you can see these certain energy spacings. It cannot take any arbitrary form of energies. And also look at that. Energy also depends on M, right? So if you make the M very big, all these energies will be very low, right? And also the difference, the spacing between the energies, they will also become very low. Okay, so these are the two impacts, which is why only for the quantum case, we see these strange energy discretizations. So we have seen two impacts. One is if you make this well wider, these energy levels will come closer. It will actually make a continuous form of energies. If you also make, let's say, the well depth smaller, like this, if you make them more and more shallow, you will also have the same impact. All these energy levels, they will come closer to each other. And at one point, there will be no difference between one energy level and the next energy level. Okay. So these are the two stuffs that we can look from this simulation. There might be another interesting thing that you may take a look. So look at the extent here, the wave functions extent. Right now, it looks like that the wave functions, if you just eye gauge, you might see that the wave, the first wave, it ends pretty much where the boundary begins. Okay, so this is the boundary, and this is the corresponding wave, right? And if I reduce the depth of the well, you will see that this guy, it will go spread around a little bit. So keep watching. I will reduce the depth of the well and look at these wave functions. What's going to happen to it? Do you see this? It's getting expanded. Is it visible? You can come closer if you have trouble. So the moment when you reduce this energy depth, this wave is going to expand. It will go and leak out more and more. Okay. Why they will leak out more? How do we know from these equations? It's because of this. Inside the well, the psi has the function that looks like the following. And outside, the wave function look like the following. Where alpha is related to the difference between potential well and the energy. Okay. So the potential is denoted by, let's say, V equal to V naught. And let's say your electron has an energy of E. So the moment you go outside, your alpha, it indicates that how fast the wave function attenuates. So if V minus E is very high, your alpha is going to be also very high. If alpha is very high, this means with this exponential function, it's going to decay very fast. Okay. So if you make this depth very shallow, that means you bring your V naught to very shallow, then this V is going to go down. That means V minus E is also going to go low. That means alpha will go low. So if alpha goes low, then this exponential function would spread out even further. Okay. So this is the reason when you make these well wider or deeper. So when you will make the script, I expect that if I give you some certain potential well, you will be able to generate all these different energy states. Okay. You don't have to make an interface like this. Like it will take quite some time to get up to this point, but you can make it static. That means if you provide a potential well, then your script can generate what are the corresponding energy levels, okay, and what are the corresponding wave functions, okay. This one is interactive, so it takes even more time. Like you can actually drag and drop something. I don't think that we have time to do this. Yes.
Do you care what language we use? We use
Yeah, anything.
Okay.
Anything. So the end product really matters, not in which way you go. Does it make sense that what we're trying to achieve here? Okay. So this is one thing. And yeah, so please take your seat. Thank you so much for coming.
I noticed you didn't have a specifically posted. Is there a timeline that you're expecting?
So break coming in, right? There is a winter break also, right?
Winter break happened.
Oh, not winter break.
Fall.
Spring break, right?
Spring.
It's in March. Okay, so what if I set a deadline of let's say post break? Would pre-break help you or post-break help you? Like, which one is more convenient? Either one? Post-break? All right, so make it post-break. So that means the week right after your break would be the deadline for this project submission. All right. So in order to make this project, you have to use some numerical methods. Like finite difference method, and in the project descriptions, I shared some videos that talks about that how finite difference method can be used to solve a second order differential equation. Okay, so look into that. It shouldn't be very difficult, but if you find some troubles, I'm always here to help. Okay, so just show up and we'll discuss in the office hour. All right. So let us now discuss about this phenomenon where instead of just one quantum wave, what if we have two quantum? So we discussed about a single quantum wave. But let's say that we have actually two quantum wells. Remember that all these wells are created by protons or nucleus. Right? So if I bring two protons close to each other, they will create two quantum wells. So how the waves of electron would look like in an arrangement like this? I know that in case we have a single well, the wave would look like this. It will have forward and backward waves inside the well, and outside the well, it will exponentially decay. But in case of two wells, it not only exponentially decay, it can actually exponentially rise also. Okay. And in fact, it would look like the following. So you see that the electron's wave functions, it takes a bulge inside every of the wells. Let's say both of these wells are exactly similar and they are separated by some distance. Okay. So let us say that this distance is W. Then if the W is very wide, that means if all of these wells are far away from each other, then of course you don't need to worry too much because they are not impacting each other. But if you bring those wells close to each other, then the wave functions of each of these wells is going to impact each other. Okay, so how do I make sense out of it? We talked about the boundary conditions in last class, and we say that we can think about boundary condition as like a junctions or a intersections of a road. If I tell you that you want to go home from campus, then you have to cross some path, reach the intersections, and then from intersections, you take another path, go to your home. So if I just tell you what is the velocity of your bike in all of these two roads, you still need additional information, like what is the property of the intersections, right? Because depending on how fast the intersections can transport vehicles, your ultimate speed and velocity, everything will depend on it, right? So now, let's say instead of one intersections, let us say that the intersection has an ability to pass 10 vehicles every second. Okay. So I give you the problem again, you solve it and find out that how much time do you need to go to your home if you want to take this path, go to the intersection and eventually reach your home. But let's make this problem a little bit twisted. Let's say instead of one intersection, I have two intersections. Okay. From your campus to your home, you take a path, go to one intersection, and then take another path, go to another intersection, and then eventually go to home. And if I tell you that the ability of traffic transport of first intersection is, let's say, 5 vehicles per second, and the second intersection is, let's say, another 5 vehicles per second. Do you think that if I put those intersections close to each other, they will still have the same ability of transport, or they are going to impact each other in some way? What do you think? Is my question clear? So the intersection, when they work alone, they have an ability of passing 5 vehicles per second. If I put two such intersections at some space, will they still have the same capability of transporting, like 5 vehicles per second, or it somehow depends on what is going on with the other guys? What do you think? Or let's make it in a bit different way. Let's say that one intersection is carrying 5 vehicles per second. Another intersection is carrying 10 vehicles per second. So they have some difference in their capability. If I put them together, will they still have the same capability or different capability? Because they will interact each other, right? So what is going on in intersection 1 would become a function of what is going on in intersection 2, right? In a similar way, when we talk about the boundary conditions, if you bring two wells very close to each other, so think like that this is one intersection and this is another intersection. If you bring those wells very far away from each other, then they won't make an impact to each other because the wave function is going to exponentially different. But if you bring them close to each other, they will start to impact each other. Okay, so it's like those intersections. Okay, if you bring them close, the impact of one would be seen by the performance of the other. So when we try to solve a system where there are two potential wells, the wave functions would also change a little bit. Okay, you will see that while the wave functions of an individual well, isolated well, have some certain form, if you bring another well close to it, this wave function is going to change a little bit. Okay, and the amount of change depends on how close these wells are. Okay. How do I give a better explanation of that? Let me try to think about a mechanical system. How much time do we have? 1 minute or 7 minutes? Okay. So yeah, maybe we can make it. So I gave an idea of about the intersection. Hopefully it gives you some very rough concept, but let's try to get into a little bit more details about it. Let's say I have a mechanical system made of a spring and a mass. Okay, this is a mass, and we have a spring. The spring has a spring constant of K. Okay. So if I let this mass oscillate back and forth, you know that this system won't have any arbitrary frequency. It will oscillate at some particular frequency. Do you know this? That if I have a spring and mass system, it cannot have any arbitrary frequency of oscillation. It has some certain resonant frequency. It will always oscillate at that particular resonant frequency. If you push it and let it oscillate freely. So how do you find out the resonance? You have to solve the Newton's equation, which says that the total force on this system is, Newton's law says F equal to ma. So I can write ma, and I can also write the other force, which is Hooke's law, which says the force on the spring is kx. Okay, remember x is the displacement from the equilibrium position. So the first part comes from Newton's law, which says force is equal to mass multiplied by accelerations. That's d square x by dt square. And the second part is kx, which comes from force Hooke's condition, that if you apply force on a spring, then the amount of force would be equal to the displacement multiplied by the spring constant k. Okay. So if you consider that this guy is going to oscillate back and forth, I can assume that x is going to take a form which looks like x naught sine omega t. And if you plug back all these numbers here, you'll get the following. Omega square would be mass x plus kx, and eventually you will see that the value of omega is equal to root over of k divided by m. Okay. So this is the resonant frequency of a spring mass system. And you can see the resonant frequency depends on two things. What is the mass and what is the spring constant? Okay. If you take the mass heavier, if you take a heavier mass, then your frequency is going to go lower. Okay. Now the question is, what if instead of just one spring mass, I take two different spring mass? Yes, these also have a mass of plane, and this is K, spring constant, and they are not separated. Actually, I connect them by some another spring. Let's say this third spring has a spring constant of C. Okay. Let's say both of them, before connections, they have the same kind of frequencies. But after you make the connections, how the new frequency is going to look like? Do you think that they will still have the same resonant frequency? Or do you think it will be something different? Remember, it is something different. I mean, even the plain eye would tell you that you have introduced a new parameter, which is C, right? This C is actually the spring that connects both of these mass. So this C must have some impact on it. And if you work it out, you'll see that because of this C, I'm not going to do the detailed math, but I will tell you the final answer. You will see that omega, instead of having a single value of K over N, omega will have two different values. One is K plus C by M, and another is K minus C by M. Okay? If you work it out, you will see that omega will have two different values, K plus C and K minus C. Okay, remember that both K and C, these are spring constant. C is just the spring constant that connects both of these guys. And K is the spring constant. So frequency will be split into two different parts. K plus C and K minus. In a similar way, if you take quantum waves and bring two quantum waves close to each other, you will see their wave function, which has a wave vector of K, they will have two different values. And depending on how close you bring them together, they will have, let's say, K plus delta and K minus delta. Okay, so that will be the impact of another wave if you bring them close to each other. In next class, we will see some more details on it, but that's the basic idea, that if you take two different systems, they both oscillate, and you somehow make a link between them, they're going to be impacted. And because of that, they will change their resonant frequency. In case of quantum wave, they will change their wave vector. Okay. Remember that if the wave vector changes, wave vectors are directly related to the energy. Right? So if the wave vector changes, the energy will also change. Okay, you will see that the energy would also be split into two different values. Okay, next class we will see some more details with some animations. Thank you, guys.